So good morning, everyone. So welcome to this GRIFE Young Scholar Seminar Series 3. Let me introduce myself. I'm Professor Bill Yan from the Department of Science and Environmental Study at the Education University of Hong Kong. So it is our honor today. Actually, we have invited my PhD student, Mr. Richard Yang, who is going to share with you actually his expertise in drone for STEM education. Let me introduce a little bit about Richard. So Mr. Yang is actually a very experienced secondary school chemistry teacher. And then, he has been teaching in secondary school for, I think, more than 20 years already. And then, and sometime actually he developed himself into an expert in STEM education using drones. And then at some point, he actually studied a master's degree in our university on STEM education. And finally, he was enrolled in the PhD degree. But Richard is actually very powerful. So you can see that actually he is an expert already. So that's why today it is our honor to actually listen to Richard to see actually how he used drone and also the generative AI enhanced stimulation to do STEM education. Okay, so without further ado, let's welcome Richard.
Okay, so thank you for Professor Yuan's introduction. And good morning, everyone. And thank you for being here today. My name is Richard, and my research focuses on advancing STEM education through the integration of drone technology. Today, I would like to guide the discussion around three key themes that shape my work: drones, Gen AI, and STEM education. Together, these concepts form the foundation of my research and the lens through which we will explore new possibilities for teaching and learning. Over the next 30 minutes, I will guide you through three main points. First, we will examine the conceptual framework behind a drone-integrated STEM curriculum and how it was designed to foster guided inquiry-based learning. Second, I will demonstrate how GenAI has been applied to create interactive simulations that enhance this curriculum. And finally, I will share our preliminary results and highlight the key findings that emerged from the study. At the heart of this curriculum is a programmable quadcopter, the Telo drone. The cross-disciplinary nature provides a lateral bridge across the different pillars of STEM. For example, it merges science and technology, as students must understand the flight principles to pilot the drone effectively. It bridges mathematics and science when students experimentally measure variables such as the camera's angle of view to connect theory and practice. Also, it fuses technology and mathematics as they design complex polygonal flight paths that require precision and creativity through block-based coding. Finally, the E in STEM comes alive as students tackle a culminating design mission, applying all their knowledge in a hands-on challenge. Our curriculum is structured in three progressive stages. Stage 1 focuses on introducing core concepts from science, technology, and mathematics individually, while using the drone as a central unifying theme across all lessons. The aim here is to establish a strong foundation in each discipline. To ensure relevance and coherence, we conducted a curriculum mapping process that aligned our learning content with official curriculum guidelines in science, mathematics, and technology education. This stage builds directly on what students have already learned in their regular classes, transforming power knowledge into hands-on experiences. Through guided inquiries, students apply concepts in meaningful real-world contexts. From the foundation, we move to the second stage, interdisciplinary integration. Here, the discipline boundaries begin to blur as students learn closely linked concepts and skills from two disciplines simultaneously. This integration happens through three distinct but interconnected learning modules. In the science technology module, students don't just learn how to fly the drone. They explore the scientific principles of lift and aerodynamics that explain why it flies. In the mathematics science module, they move beyond theory to conduct hands-on experiments, using mathematical formulas to calculate the drone's actual flight speed and other physical properties. In the technology mathematics module, they apply geometric principles and logical thinking to program the drone for precise autonomous navigation, turning abstract mathematics into a real-world flight plan. The peak of our curriculum is the final stage, trans-disciplinary application. This is where all the foundational knowledge and integrated skills converge. At this point, students are no longer simply learning concepts. They are applying them as engineers and innovators. Their capstone mission is to address a real-world challenge, designing and building a drone-assisted water sampling system. This mission requires them to engineer a physical mechanism capable of collecting a water sample, program the drone to perform an autonomous flight to a designated location, and also execute the collection and ensure the safe delivery of the sample. In this module, students truly embody the spirit of STEM by using knowledge across disciplines to create a practical solution to a meaningful problem. We translate this conceptual framework into practice through a 12-hour course, delivered across 8 1.5-hour lessons. This curriculum is carefully scaffolded to guide students step by step through an inquiry-based learning process, ensuring that each lesson builds meaningfully on the last. However, our pilot implementation encountered several practical challenges. We observed students struggled with abstract concepts such as flight physics. Piloting physical drones involve risk and cost, including maintenance and high battery consumption. The process of refining code for flight path proved time-consuming and inefficient. This is where the GenAI became a game changer. Despite having no formal programming background myself, I was able to use the large language models to translate my pedagogical goals into HTML code. By describing the learning activities I needed in plain language, we developed an online platform with 11 interactive simulations to directly address these challenges. The following video provides a brief overview of the platform, and more importantly, showcases students actively engage in these virtual and physical learning scenarios. To evaluate the effectiveness of this Gen AI-empowered curriculum, we conducted a study with 227 students from grade 8 to 11 across 14 secondary schools using a mixed methods approach. For our quantitative analysis, we measured learning gains using a STEM knowledge quiz and surveys on 21st century skills and computational thinking administered as pre- and post-test. We then analyzed this data using pair sample t-tests to identify statistically significant improvements. For our qualitative analysis, we sought to understand the process of learning. We collected students' post-lesson reflections, where they describe their problem-solving experiences and challenges. This data was coded and analyzed using epistemic network analysis, ENA, to visualize how their thinking align with the curriculum scaffolded design. We code students' discussions for their learning behaviors across 4 domains: conceptual knowledge, procedural skills, high-order thinking, and affective and metacognitive skills. The resulting ENA model proved to be statistically robust. With a goodness of fit value of 0.98, the model provides a highly accurate map of connections. It explains 28.7% of the total variance, meaning it effectively captures a significant portion of the patterns in student learning and thinking. Think of the ENA output as a map of learning. The horizontal y-axis represents a progression from concrete hands-on experience on the left to more abstract, technologically driven thinking on the right. The vertical y-axis represents a shift from individual reflection and engagement at the bottom to collaborative critical inquiry at the top. These 2 axes created 4 distinct learning zones. The lower left refers to engagement and early reflection. The upper left refers to experiential inquiry. Upper right, the technological inquiry and collaborative design. And the lower right refers to the identity and metacognitive reflection. The 16 nodes, each representing a learning behavior, remain fixed in position across all maps. This consistency allows us to track how the connections between ideas and the permanence of certain skills evolve from one lesson to the next. Now, let's look at the network for the first lesson. In lesson 1, the network is centered on the fundamentals. The dominant nodes are affective engagement, basic piloting skills, and operational knowledge. At this stage, students are excited and focus on learning the how-to. But lesson 2, the center of gravity shifts. Piloting skills remain present, but the focus moves towards problem solving and applying abstract knowledge. Entering the mathematics science module in lesson 3, the network shifts again, becoming dominated by collaborative learning, problem solving, and critical thinking. As we progress through the middle of the curriculum, the learning became increasingly sophisticated. In the subsequent mathematics and technology modules, the network's gravity pulls strongly towards the upper right quadrant, the zone of the technological inquiry. Across these lessons, 3 key skills emerges as consistently dominate. The first, technological and computational thinking as students master block coding. Critical thinking as they debug their complex flight paths. And cross-disciplinary application as they fuse mathematics and programming to achieve their goals. At this point, students are no longer just using the technology. They are commanding it with logic and critical thought. Finally, in a capstone engineering mission, the network makes its final shift into the lower right quadrant. Here, the focus transcends technical skills and moves into higher order synthesis. The dominant nodes become metacognitive reflection as students evaluate their own design process, STEM identity as they see themselves as real engineers solving authentic problems, and cross-disciplinary application at its highest level, integrating knowledge and skills across domains. When we plot the centroid of each lesson's network, we see a beautiful and clear learning arc. It begins in the lower left with engagement, move upward into the experiential inquiry, shift across to technological design, and finally lands in pedagogical reflection. This visual story perfectly mirrors the scaffolded design of our curriculum. Crucially, this qualitative journey is validated by our quantitative data. Pair sample t-tests confirmed statistically significant improvements across STEM knowledge, 21st century skills, and computational thinking. The ENA story is backed up by the numbers. So, what can we conclude from these integrated findings? First, the curriculum works as designed. The ENA learning arc provides clear visual evidence of a scaffolded progression from foundational knowledge to higher order and to metacognitive thinking. Second, students develop the right skills. Quantitative results show significant gains in critical thinking, creativity, and computational thinking, the exact competence we set out to foster. And perhaps more importantly, our study fostered a new model for curriculum validation. By combining process-level ENA insights with quantitative outcomes, we have demonstrated a framework that creates a holistic picture of learning. Our next step will be using this framework to analyze cognitive shift across different genders and grade levels, further deepening our understanding of how students learn. If you would like to explore this work further, I invite you to access our recently published bilingual handbook on drone-based learning. It contains our complete research plan, framework, and teaching materials, all available for download. For a more academic perspective, I encourage you to read our two recent papers, which examine the research behind this project in greater detail. Finally, I will be delighted to continue this conversation. Please connect with me on LinkedIn. I welcome any further discussions or opportunities for collaboration. Thank you for your time and attention.
Hey, thank you, Richard, for the presentation. Maybe we can have some time for Q&A session. Let's see if you have any questions for Richard. You can either switch on your microphone or type it in the chat room.
Yes. Can you hear me?
Yes, Mr. Lam. Yes, please.
Yeah. I'm also from Education University, Hong Kong, actually from the CNI department. I'm I appreciate very much the presentation because it gave me a very informed introduction of how STEM can be implemented, okay? Because I'm a layman. I'm a layman to STEM, but I can see how this project developed from the very curriculum's perspective, very in-depth and logical kind of development. But I want to know any implication for the hiring of teachers in terms of implying this kind of STEM education. How will you suggest hiring the teachers if you want to do some STEM education like this? Okay, my layman question. Okay, yes.
Thank you for the question. Because as Professor Yuan introduction, I was a secondary school science teacher for long years. I think the biggest challenge for us to develop STEM curriculum is to find an appropriate medium to link up multiple disciplines. And in my project, I suggest drone technology as the common theme to link up the multiple disciplines, but it is not a must because you can choose anything if you can connect to the content selected from the curriculum guides. So I will suggest to frontline teachers that the first thing is you have to choose an attractive enough technology for students to engage. And particularly in our implementation experience, students feel excited because of the medium and they are willing to engage in a deeper learning. And that's why they give so many responses in their reflections. That's the first thing. And however, I must share that in my old days, I spent lots of time to explore these possibilities. I have to try to spend a lot of time to do many kind of experiments. What I share with you is the successful one. And I spend a lot of time to produce failures, So teacher must be ready to spend a long time to test and experience the difficulties when they learn something they're not familiar with. Because no one will be familiar with drone technology. And none of the teachers are STEM majored. They just single discipline major, right? So there's a great challenge for them to find a medium they are interested in and also spend time to test.
Yes, thank you. Thank you very much. Okay.
Thank you.
Do you think the engineering teachers will stand an advantage in your project? Engineering student, okay.
I think so. According to my observation, in many schools, the STEM education is mainly developed or in charge by engineering background teachers or ICT background teachers. That's the fact. Yes, they surely have the advantages.
Yes, thank you. Thank you.
Yeah.